Okay, ladies and gentlemen, today we're going to have a short discussion, relatively short, of clustering. So we studied two ways of clustering, right? And remember, clustering is all about reducing the complexity of the problem overall, right? Because the data sets, now let me also tell you that in this class, every data set that we dealt with, you probably noticed, is not a big data, right? Moreover, I probably very rarely, if ever, said the words big data. These days, big data is a buzz term, right? You can hear it from everywhere, right? You go on the internet, it's all about big data and Internet of Things and Hadoop. You probably heard the term Hadoop, right? Hadoop basically is the open source technology that allows you to deal with data sets that are too big to reside on one computer, on one hard drive, right? So this class is not about the big data. This class is about small data, if anything, right? All data sets that we were dealing with. How many observations did we have in each data set? Probably 100, maybe 500, 1,000, right? The project that you dealt with, delayed flights, how many observations did we have there? 20, 200 or something like that, right? So it was no more than 10,000 observations. This is small data. Okay? When you're dealing with big data, we're talking about billions of records potentially. Okay? Millions, that's for sure, potentially billions of records. That problem becomes very complicated. All kinds of records are in the data set, right? So therefore, what clustering is about is simplifying things a little bit. For example, let's say I collected information on, I don't know, 5 million customers, right? You're running regional supply chain, okay, with 50 different stores, and you have millions and millions and millions of customer records. But you want to create customer profiles, okay, in order to market things to customers more effectively. What do? Well, you slice the data set into similar records, and then you try to see if these similar purchases will tell you something about who is the typical customer who makes these purchases, right? Is there anything in common between them? Are they all males or females? Maybe they have certain income, right, higher than certain level. Do they own the house or do they rent the house? So you create sort of a personality, right, marketing personality. And you say, this personality corresponds to this type of purchases. That's what they do most frequently. So let's actually take a look at how you can kind of evaluate clusters that you create in order to see if you have a reasonable thing or not. So go ahead and open up JUMP. And let's go to the data library that we always use, sample data library from the help menu, okay? And in the help, in this data library, let's find a file which is called serial. Do we have serial file? Yeah, right there, serial jump. Did you find it? Cereal. Do you like cereal? In the morning? Yeah, a lot of people eat cereals, right? So, here is the data set that contains, 76 different cereals, right? Okay. And each cereal, so the idea basically is, can we see if some cereals kind of belong together, right? In terms of their characteristics. And what characterizes cereal? It's all about nutrition these days, right? When you buy a box of cereal, there is a label that gives you the summary, right? It says per serving, and what by the way, what does it mean per serving? What's a serving, typically? A bowl, right? Maybe. Most people don't measure things, right? Typically, when you make cereal in the morning, what do you do in terms of like how much do you put in the bowl? Just let it go, right? Do you pull out this thing that's called cup and then 1 cup, 2 cups, 3 cups? Do you do that? No, you just basically dump it, right? And when you think you have enough, that's it. And then some milk and go, right? So nobody actually measures things by the cup or half cup or whatever it is, right? But in most of cereal boxes, the nutrition information about that cereal is on the per serving basis. Typically, it's a cup, right? So, what kind of things can we be as a nutritionist, right, or nutrition conscious consumer, right? Can we be looking for? Well, here, right? Calories, and that's typically per serving, right? Calories per serving, amount of protein, amount of fat, and then calories from fat, right there, okay? Then fiber, sodium and potassium. You know that sodium and potassium in the body are in the balance, right? Together. So these two are what's called electrolytes, right? Sodium and potassium are very important because sodium is, I believe, is it water retaining mineral or water retaining, right? Sodium is retaining. So if you eat a lot of salt, right, that means that you retain a lot of water, right? You feel puffy, you gain weight and all that stuff, right? So don't eat a lot of salt. Potassium does opposite, right? It basically drains the water out of the organism, right? So these two are in balance, right, with each other. Then there are carbs, right? It says carbohydrates, right? Complex carbohydrates and total carbs. And then there are sugars. Then what else? Weight per serving, cups per serving, whatever that means, right? Okay, so let's see if we can find clusters. Well, we can't find clusters. It's a matter of applying the algorithm, right? But can we interpret clusters? Remember when we had this discussion, we said what's kind of important is your capability, not only when you get a cluster, so these things are together. Yeah, cool, but what's about this cluster, right? How should we name it? So let's do this. I'm going to go to Analyze menu and do the clustering. So let's start with hierarchical, and then we'll see what k-means gives us, okay? Hierarchical clustering. So how about that? I'm going to select all the variables which are numeric. Numeric means blue triangle, right? So things that I measure numerically. You can see that there are others, right? Such as name. Do I want to cluster them by the name? Do I want to use name as one of my variables? Probably not, right? It doesn't make it. Manufacturer. It's another thing that's probably not important, right? MFR, don't know what that means quite honestly. Hot or cold, that's probably not informative. And then enriched, yes or no. These things I'm going to skip, right? So weight per serving and cups per serving. So I'm going to include all things that are numerical about my cereals, right? And these are all just variables or dimensions, right? About each cereal, we're going to use these measurements. So I'm going to just add them all together, right? Click OK, and then it goes to the agglomerative procedure, and there it is, right? It gives me how many clusters I have right now. Let's see. If I click right there, it is cool looking. So right now I have 8 clusters, right? Okay, well, 8 might be a little too much for me. I don't know. Let's scale it down. Let's see if we can make sense out of fewer clusters. So let's kind of drag it right there, and let's leave it at 3. So I'm going to cluster them at 3 in 3 different groups, right? And let's color the clusters so that we can see. This is my cluster 1, the red part. This is my cluster 2, the biggest probably, and that's my third cluster. Okay, cool. So here is what we were trying to do in the previous class unsuccessfully, okay? What I can do is go ahead and try to find cluster summary. So let's call up the cluster summary. And here is the summary. Let's take a look at means. So what it does basically, the software for us, is all cereals that were grouped, clustered together, they have measurements, right? We have many different variables, protein, calories, fat, sodium, etc., right? It takes all the cereals in one cluster and calculates the average measurement for them. Average fat, grams of fat per serving, right? Average sodium, average potassium, sugars, etc., okay? So, therefore, I have 3 clusters, and I have 3 means for each of the measurement, right? For potassium, sodium, fat, calories, carbs, etc. Okay, so I can kind of click through them. So when I click on one of the clusters, it's being highlighted. And what this graph represents right there, it's basically a plot, okay? Plot of all of my averages. So all clusters are right here, okay? And I can click through them and kind of see how they evolve. You kind of can see that the colors are not very pronounced, right? Can I edit the colors? Just out of curiosity. Row colors. Can I make it black? Oh, look at that. I can edit actually things. I didn't know that. Cool. All right, so that's my number 3, right? Okay, so as I click through the clusters, and I can kind of visually see how they line against each other, right? I would like to name them. Why? Because one cluster, what's so special? Why did we group these items together? What's so special about them, right? So look at that. If I flip between cluster number 2 and cluster number 3, what strikes you? If I go back and forth between 2 and 3, what do you see? What happens? Visually.
The highlighted line changes.
What?
The highlighted line changes.
Well, highlighted line changes, that's right.
Like the colors, like under the background, they also switch.
Well, but what I'm talking about is this thing right there. So, what do you see? What's the behavior? So this is my first group, and this is my second group, right? So in general, cluster number 3 is what? Has higher measurements than cluster number 2. Would you agree? Yeah. So if I click on the cluster number 2, it's kind of it's low on a lot of measurements, right? So let's take a look. For example, calories, right? In terms of calories, it's kind of close to the low calories. Would you agree? Yeah. It's lowest in protein, right? It's lowest in fat. It's lowest, not in sodium, right? It's kind of medium, right? It's lowest in the fiber. It's kind of low in carbs as well, right? Just like cluster number 1 and cluster 3 is kind of high, right? Then carbs, it's also kind of low on carbs together with 1, right? Sugars, it's kind of in the middle. Calories from fat is the lowest. That's probably because fat is lowest as well, right? Low fat, low calories from fat. That makes sense. Okay. What else do we have? Potassium. Very low on potassium, right? It's low on, no, it's not low on sodium. It's low potassium, right? So I can actually kind of take a look at how does that cluster, on all measurements, how does it compare to the rest of them, right? And then I can call this cluster low fat, right? Low protein, low fiber as well, right? Low calories from fat, obviously, and also, what did we decide? Is it low potassium? Yes, it is, right? Low potassium cluster, okay? So these are all the cereals that share this characteristic, okay? All right. Then cluster number 3, let's take a look. Cluster number 3 is kind of high, right? It's highest in calories, it's highest in protein, it's highest in fat, it's highest in sodium, kind of high in fiber, right? The previous cluster was low in fiber, that's kind of high. It's highest in carbs, it's highest in total carbs. So it's high everything, right? Including sugar, including calories from fat, and high potassium. So every single thing that probably we can imagine, right? Sodium, potassium, fat, proteins, all of them, right? It's a really high, nutritional content kind of cluster, right? And how about cluster number 1? Well, cluster number 1 is a little bit mixture of everything, right? So let's see. It's low on some things and it's high on some other things, right? Calories, it's the lowest, right? Protein, kind of high, right? Fat, I can say that, it's low sodium as well, right? Potassium, kind of in the middle, right? It's low sugar. It's also low in the total carbs, and it's low in complex carbohydrates, okay? But it's highest in the fiber. So, therefore, I can basically kind of isolate the characteristics of each cluster and say, hey, this is low sodium, high potassium, low carbs, high fiber cluster, right? Another one has different characteristics. So after that, I can essentially kind of, by naming my clusters, I can essentially, point out important characteristics, right? What stands out about that cluster compared to other ones, right? And after that, every cluster, every new cereal that is going to go added to the market, I can just go ahead and see where it belongs, right? So now I have 3 clusters, right? I can calculate, so to speak, difference between that new cereal and cluster number 1 centroid, cluster number 2 centroid, cluster number 3 centroid. And therefore I can say, the lowest distance is between this new cereal and cluster number 2. So therefore, that one becomes low fat, medium sodium, blah blah blah, whatever the characteristics of my cluster is. Okay, make sense? So I don't just hey, here's clustering, right? Hey, good. How do you use this, right? How do you use this information? Okay, so that's what we can do with hierarchical clustering. You know what? Let me show you something else actually. Some other idea, okay? And just for illustration purposes, nothing more than that. Let's go ahead and do the same exact thing, clustering, but using what's another method that we learned in clustering. One was hierarchical, another was k-means, right? With k-means, I'm telling the software how many clusters I'm going to end up with, right? And then it finds the centers themselves, right? And does the clustering, okay? All right, so let's do the same thing. So analyze, clustering, k-means. I'm going to do the same thing. Select all things numerical, right? All the dimensions that I'm using. So basically my blue triangles, right? And then add them to the columns. Click OK, and there it is. And let's do the same thing. Let's see if I can cluster things differently using number 3, right? So I click Go, and there it is, okay? So it does pretty much similar procedure for me, except, of course, I don't aggregate things, right? In agglomerative clustering, what happens is I start with every single point, and I start kind of merging them together, right? And clusters grow and grow and grow, and that happens naturally. Here, I'm basically kind of starting with 3 random points, right? I know that I'm going to end up with 3 different groups. So random point 1, 2, and 3, and then closest points come together, and then I recompute the centers, recompute distances, reallocate points again, form new clusters, and repeat that thing until it stops changing, right? That's the idea. Okay, now this one, I don't think it gives us much of the visual tool, actually. At least I didn't find, like, if you do the biplot, that's your biplot, okay? But biplot, let me show you what biplot really is, okay? I kind of found that, well, it's not what I'm about to show you is not informative at all, okay? But it's kind of, it's a cool picture, okay? Biplot is a 2-dimensional projection of a 3-dimensional picture. Let me show you what that is, okay? So if I go to this rectangle menu, I can show you, I can demonstrate biplot in 3 dimensions. Typically, when it comes to the computers, 3 dimensions is not very good representation, to be honest with you, right? Like, for example, you probably heard that one of the, I don't know if you heard about that or not, let me see. What's the worst type of the chart to put in your graphical presentation? It's like common, it's not exact science, of course, but people who are considered to be experts in visualization, it seems like they commonly believe that this chart should be avoided always. What type of chart? Pie. Pie chart always is like, no, you don't use it, okay? It's cute, maybe, right? Hey, here's 100%, let's slice it. Here is 30%, here is 27%. But pie chart is probably the worst visual presentation of data. And what can be worse than pie chart? 2 pie charts, right? No. There is such thing as 3-dimensional pie chart. Have you seen the 3-dimensional? It's like, it's a pie, right? If you look at it from the side. That is even worse, because if you're like looking at the pie chart from the top, right, you can at least judge the sizes of the slices, right? If it's 3-dimensional, it's kind of viewed at an angle. That effect is gone completely, right? So it may be looking cool, but it's as useless as it gets, right? So 3-dimensional plots in the computers are pretty much the same, okay? Useless. So this is useless thing, right? But you can hook up like the one of the corners and try to rotate it. Let's actually try that. Can I do that? Yeah, look at that. If I rotate this thing around, you can see that I clearly have 3 clusters, right? So clusters, and are they nicely separated from each other? That was one of our ideas, right? How do you know if clustering that we performed is actually good clustering? Well, if clusters are clearly separate from each other, they're separated. That's actually a good thing, right? What happens if clusters overlap? That means that points in this common intersection piece, how do you classify them? Over here or over there? That's kind of a little bit, it sucks, right? Yay. All right. So, take a look at the, well, we have 3 dimensions, right? What is our x, y, and z? What does it say? Preen 1, preen 2, and preen 3, right? Well, natural question is, who is preen, right? Print, ladies and gentlemen, is something that's called principal component. Okay? Here is the idea. We're not going to do that in this class. I'm just going to kind of announce that, sort of, right? Ooh, look at that. Okay. All right, here's the idea behind the principal component. Okay. Remember when we discussed clustering, the intuition behind clustering is to take this gigantic data set and try to slice it into still big pieces, but they will group things together, right? They will group similar observations together. That's the idea behind clustering. So in other words, simplify things, right? And if you kind of think about our data set as a table, two-dimensional table, right? Here are my columns, right? Columns are also called what? Variables, right? Variables. And rows are my observations, correct? Every observation is a record, right? An observation has multiple measurements, right? Such as, for example, fat content, sodium, potassium, calories, blah, 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 all these things. Sugars, carbs, right, etc. That's my columns. But every row has all these numbers, measurements, right? So clustering basically deals with this part, right? I'm going to group these things together. I'm going to group these things together. Can I do the same thing with rows? I can, right? It would be nice. Oftentimes what happens is your data set not only contains a lot of records, but it also contains a lot of columns, a lot of variables. Remember when we discussed overfitting? One overfitting happens when you throw too many variables at the model, right? You throw additional variable, R squared goes up, right? But what happens with adjusted R squared? At some point it starts declining, right? Why? Because the model becomes too complex and you get punished for that, right? Basically, the rule of thumb here is if your model is simple, it's good. Simple is good, complex is bad, okay? It should be interpretable. The ultimate users of this model are going to be managers, right? They don't like complex rules. If customer is between age 47 and 49, and they've been married more than 7 years, and their income is between $65,000 and $67.5 thousand. What? Right? You're slicing things too fine, right? It's a lot of ifs, okay? I want something simpler. I want something that I can apply easier, okay? So sometimes we want to group some variables together. And that's what principal component is all about, okay? Principal component basically saying, okay, fine, we have variable x1 in this column. We have variable x2 in this column. Here is x3 and here is x4. In order to build a model, can I combine some of the variables together and create a new variable? In other words, let's say that this is my, here, good example. How doctors, if you know this thing, how doctors can tell if your weight is normal or you're overweight or you're plain fat. What do they calculate?
Is that the BMI?
BMI, right? Have you heard about BMI? BMI, what does it stand for? Body mass index. You know what's the formula? Quite honestly, I don't remember it. I believe it's your height divided by your weight squared. That's the formula. Okay? So, in other words, when patient comes in, they measure your height and they measure your weight, but they don't use height and weight separately. Instead of that, they combine them together to create a new thing, right? BMI, body mass index. So, the idea behind the principal component is this. Instead of using, for example, let's say that this is my house, I'm going to create, here, good idea, kind of struck me, sometimes it happens. Let's say I want to predict the price of the house based on, so this is my y variable, based on square footage of the room, of the house, number of rooms, and the land size, right? I believe we discussed this one. What do you expect in terms of correlation between number of rooms, square footage, and the land size? Do you expect them to be highly correlated or not so highly correlated? Highly correlated, right? Why? Because if you have a large house, what does that imply about number of rooms? A lot, right? If you have a large house, what does that imply about the land? A lot of land, right? So these things probably go together. So there should be a high correlation between them. And what will happen if we put all these variables in the model? Remember what kind of problem that creates when you have highly correlated variables? This is called multicollinearity, right? Multicollinearity can create all kinds of weird effects. So instead of that, here's what I can do. I can say, you know what, square footage and number of rooms and the land size are highly correlated. I cannot use them together in the model simultaneously because they tell me the same exact story. But how about this? I'm going to say, well, let's take square footage and let's take number of rooms and let's take land size, okay? Land. These three things are separate variables, right? But here's what I can do. I can multiply that by the number, whatever number it is, alpha. I can multiply that by whatever number beta, and that one by number gamma, and add them all together. And use that as my new variable. Can I do that? I can, right? It's going to be a weird variable, right? You take the square footage, you add rooms, you add the lot size, you mix it together with some weights, right? And out of that you create a new freaking monster, right? But who cares, right? The only thing that I care about is, will I be able to accurately predict the price of the house or not, right? If it needs to be done, let's do it, right? I'm fine with that. Let's create this new variable. So let's say I find that alpha should be 0.5, beta should be 3, and gamma, land, should be like 0.7. Fine. Next house, let's say I'm going to build my model with this awkward new variable. Next house that I'm going to get is going to have 1,500 square feet, right? 3 bedrooms, and land is going to be 1.5 acres, okay? 1.5 acres. I'm going to just plug these values into the equation, multiply them by alpha, beta, gamma, and get this new weird looking variable, right? So that's going to be my principal component 1. If that turns out to be a good predictor variable, why can't I use it for my prediction of the price? I can, right? So I can now mix and match variables and create new things out of them, like this one. And that's the idea behind the principal component analysis. So why did I start this whole discussion? Here, print1, print2, and print3, what are they? Principal components, okay? So in other words, what software did behind the scenes, it said, let's take, for example, potassium and fat, calories from fat. Mix it together and create a new variable. We're going to call it print1, okay? Then let's take fiber content, add sodium multiplied by 1.6, and add to that sugars multiplied by 7.5, okay? We're going to call it principal component number 2. And same thing, principal component number 3, okay? So that kind of gives you a glimpse of what else can be done. That obviously opens up a whole new sea of capabilities, right, with data analytics, because out of my existing variables, I can start creating combinations of the variables, right? And if they prove to be important and useful and statistical significant and good predictors, why not use them for the modeling? No reason, right? I can totally mix and match variables, create new things that didn't exist before, and go for that, okay? Another good example actually would be, let's not go there. I think we discussed enough. So this is just FYI kind of, okay? Just to give you another look at the land of the data analytics, okay? There is a huge landscape. Data analytics has a lot of capabilities that we didn't cover in this class. Okay, so I promised you that this is going to be short, right? So this is it for today. Next class, we're going to start looking at, well, what people know as artificial intelligence and what data analysts and data scientists know as neural networks. Okay? All right.